Section 3.3, Polynomials and Other Functions. So, a polynomial is just the sum of a whole bunch of terms. Each term looks like some coefficient, some number, times x to a power, where these powers are whole number exponents. And so I have here that n is some whole number, j is some value from 0 to n, 1, 2, 3, dot, 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 up to n. A sub j is some number, could be any number in a, let's say, a field. And x is some indeterminate, some variable. Now we'll want to look and see what is the graph of these types of objects, polynomials look like. So, in general, first, I guess, let me give you a notation first. The degree of a polynomial. If the leading order coefficient, the a sub n, is not 0, so if this highest term here is not 0, then I call the degree of my polynomial n. For a polynomial of one variable, it's just the largest power in your polynomial of your variable. The largest exponent of your variable will be the degree of your polynomial. In general, a polynomial will eventually go off to either plus infinity or minus infinity. It could be both going to minus infinity or both going to positive infinity, or one going to positive infinity, the other going to negative infinity. But eventually they go off to infinity. In between, they have these peaks and valleys. Each of these peaks and valleys are called an extrema. The number of extrema will always be less than, strictly less than, the degree of your polynomial. And so if this is of degree 4, there could be as most 3 extrema. And so in this case, well, it has to be greater than degree 4, because there are 4 extrema. So therefore, this polynomial, I don't know what the degree is, but certainly the degree of this polynomial would need to be greater than 4 for it to have a graph looking like this. Okay. Let me give you, okay, so first, let's look at what happens in the first or fourth quadrant. If this leading order coefficient, a sub n, is greater than 0, then we go up, eventually, we go up into the first quadrant. If a sub n is less than 0, we eventually go down into the fourth quadrant. So if the highest order term is positive, then it goes up. If it's negative, then it goes down. If the degree is even, then we'll either both go up or both go down. And so these tails go in the quote unquote same direction. They'll either both be going up to infinity or down to negative infinity. If n is odd, so if I have a polynomial of odd degree, then the tails here will go in opposite quadrants. So they go in opposite directions. So if n is even, they go in adjacent quadrants. If n is odd, they'll eventually go into opposite quadrants. So let's just recall an even function. Even functions are symmetric about the y-axis. A function is symmetric about the y-axis if f of a function is symmetric about the y-axis if f of negative x is equal to f of x for all x in the domain of f. An odd function. A function will be symmetric about the origin if f at negative x is equal to negative f of x. Note the following, and this is why I didn't state it. A function is never symmetric about the x-axis, except for, well, one exception. The function f of x identically equal to 0. So if f of x is always equal to 0, well, that's symmetric about the x-axis, but anything else is not symmetric about the x-axis. And still being a function. An increasing function. I'll give you a nice little picture here to show you what it means to be increasing. So f is increasing on the interval I if f of x1 is less than f of x2 for all x1 less than x2. Maybe I'll say this is x1 and this is x2. Then this would be f of x1 and this is f of x2. Okay. So x1 here is smaller than f of x1 here is smaller than f of x2 for all x1 less than x2. So notice that it makes sense pictorially here that if a function is increasing, it looks like it has that property. So when we say that a function is increasing, what we do is we look at the graph of y equal f of x, and we read the graph from left to right. If, as we're reading the graph from left to right, my y values are getting larger, then we say the function f is increasing. Whereas a decreasing function, f is decreasing on the open interval I if, and now let's say we'll do x1. So this is f of x1. And let's say this is x2. So this is f of x2. Okay. So f is decreasing on the interval I if f of x1 is bigger than f of x2, which it is, it's above it, for all x1 less than x2, which it is here. And so we notice that this is decreasing if, as we read from left to right, my y values are decreasing. So again, as we read from left to right, if my y values are increasing, it's an increasing function. If my y values are decreasing, it is a decreasing function. If it's always equal to the same value, then we call it constant. So f is constant on the open interval I if f of x1 is equal to f of x2 for all x1, x2 in the interval I. So if for any x value, you always get the same y value in that interval, then f is constant on that interval. The greatest integer function. And so the greatest integer function is the supremum, the largest value, the maximum, y value, the largest integer, which is less than or equal to x. So if I wanted to find, oh, and by the way, sometimes we also denote this. They sometimes write it like it's like a almost a bold or something, double line thing. In your book, a lot of times, if you look in your book, it looks more like this. So this is the floor. So if I look at something like pi is 3.14. And so to find the greatest integer function for 3.14, well, what's the greatest integer that's smaller than, well, or equal to 3.14? Well, the biggest integer less than or equal to 3.14 is 3. And so for positive real numbers, the way that you can determine the greatest integer function is you just truncate it. Get rid of all the decimal part. So the greatest integer function of 8.7832457 is 8. So you just take the 8 and then point whatever 345. You don't care about whatever the point is. You only worry about that integer part. Okay, so that's the greatest integer function. Let me give you some properties of roots. Even multiplicity. If a root has even multiplicity, it will bounce off the x-axis when I draw the graph of it. So actually, let's see if up here we drew something. Oh, good. So if I have this, suppose a root here will be someplace where it crosses the x-axis. So in this case, suppose that this was an even root here, then notice it bounces off the x-axis. Whereas if it has an odd multiplicity, it passes straight through the x-axis. So even bounces, odd passes through. If you look locally, notice that in this small little region here, this actually looks like y equal x squared. And if you look in this small region here, it looks like y equal x. So this is really going to be a local property of polynomials near their roots. They look somehow like easier polynomials. And we'll do that asymptotic behavior also. Okay, so even multiplicity, the function bounces off the x-axis at that root. If the root has odd multiplicity, then goes straight through the x-axis at this root. So suppose x bar is some root of the polynomial, so that, well, the polynomial at the root is 0. That's the definition of root. Then p at x bar is asymptotic to some constant k times x minus x to the r to the m, where m is this multiplicity of this root. Okay, so let's do some examples. On page 321, graph each polynomial function. So we're going to, I guess, tie in a whole bunch of stuff that we've done and try to do this. So first off, I have that the degree of this polynomial is 3. The highest power here of this polynomial is 3, so it has odd degree. Okay. So that means that since it has odd degrees, these tails will be going in opposite quadrants. In quadrants that are antipodal to each other. So either the first and third or the second and fourth quadrants. Okay, so the leading order coefficient of this polynomial is 1, which is greater than 0. Therefore, we go up into the first quadrant. Let me do a new page here. So that says that we go up into the first quadrant. And, well, opposite the first quadrant will be the third quadrant. So when we do this, I want to go up into the third quadrant, go up into the first quadrant, and down into the third quadrant. Okay, so now let's simplify this. I have f of x, and I'll call it y, equals x cubed minus 16x. Factor out x. What remains is x squared minus 16. This is a difference of squares in the parentheses. So I can factor this as x minus 4 times x plus 4 using the special product formula. The product of the sum and difference of two terms is the difference of their squares. Okay, so now I've written this in factored form. So now let's try to determine the roots of my polynomial. The x-intercepts. And so set each factor equal to 0 and solve for x using the zero factor property. The fact that these are integers over a polynomial over the integers. So it's an integral domain. Add 4 to both sides of your equation. Subtract 4 from both sides of your equation. And so the roots are x equals 0, x equals 4, and x equals -4. And each of these have multiplicity 1 because the exponents here are just 1. So with multiplicity 1, having multiplicity 1, we usually call these simple roots. So each of these are simple roots. Okay, so it means that each of these are going to be passing through the x-axis at these roots. Okay. And as a matter of fact, they'll be passing through in a linear type of fashion because they're multiplicity 1. So let's try to draw this. So I have roots at 0, 4, and -4. I go up into the first quadrant, and I pass through, pass through, pass through, yeah, whatever. I guess maybe I'll just move it. Even though it doesn't look that good there. So it's -4. And so this is a graph of y equaling x to the third minus 16x. And that's what the sketch of the graph looks like. This goes, I should have gone even further down. It's not growing fast enough. Okay, there, that looks a little bit better. So that's what the sketch of the graph looks like. Okay, let's do this example, which is actually similar to a problem in the book. I just sort of modified it so I can give you an example of something. Okay, so I put some exponents here. They had these all as simple roots, so I weren't simple. The degree of this polynomial, well, 1 plus 2 plus 1 plus 3 is 7, which is an odd number. So this has odd degree. Since this has odd degree, that means that this polynomial is going to be going into opposite quadrants. The tails will be in opposite quadrants. So the tails will be in antipodal quadrants. The leading order coefficient is 1. If you look at this is x to the second, x to the third. So if you multiply this all out, you'll get 1x to the 7th plus a whole bunch of other stuff. So this leading order coefficient is positive. Which means that we're going up into the first quadrant. So the tails will eventually be into the first quadrant and the third quadrant. Okay. Just like the previous example, actually. Let me determine the roots of my polynomial. It's already nice and factored, so I can set each factor equal to 0 and solve for x. So x equals 0, x minus 3 is 0, x minus 2 equals 0, x plus 1 equals 0. So I can take the square root, so x minus 3 is 0. And this, of course, is by the zero factor property. The fact that this is an integral domain, integers over polynomials having integer coefficients will be an integral domain. Okay. Add 2 to both sides of your equation, so x equals 2. Take the cube root, so x plus 1 equals 0. Add 3, subtract 1. And so my roots are x equals 0, and this has multiplicity 1, x equals 3 of multiplicity 2, x equals 2. This again is a simple root, so multiplicity 1, and x equals negative 1. This has multiplicity 3. Okay, so those are the multiplicities. Good. So this is odd multiplicity. Even multiplicity. Odd multiplicity. And this is odd multiplicity. Let me, well, let me give you some asymptotic behavior for this. Yeah, let me just tell you some asymptotic behavior for it. Okay, so let's look what happens at 0. So near x equals 0. So near x equals 0. Well, what I'll do here is in this polynomial, if a term is 0, just leave it. So I'll leave this as x. But for everything else, I'll plug in 0. So 0 minus 3, 9. 0 minus 2, negative 2. 0 plus 1, 1 cubed, 1. And so I just get negative 2 times 9, negative 18x. And so near x equals 0, y is negative 18x. Near x is equal to 3, y is approximately, well, is asymptotic to plug in for x3. Oh, maybe I should. Actually, let me. So it was x 0 minus 3 squared, 0 minus 2, 0 plus 1 cubed. And so this is 9 times negative 2 is negative 18x. Okay. Now let's look what happens near. Oh, actually, I'll just put another line here. Let's give me some more room. So notice that x here had odd multiplicity. It was a simple root, had degree 1. So near x equals 0, it looks like a line, a polynomial of degree 1. So it looks like a polynomial of degree 1. It looks like some polynomial of degree of its multiplicity near the root. Let's look at what happens near x equals 3. Okay, so near x equals 3, we have that y is asymptotic to, has the same behavior as, well, plug in 3. If I plug in 3 for the x minus 3, I get 0, so I just leave it as x minus 3. Plug in 3, 3 minus 2, plug in 3, 3 plus 1, ooh, cubed. Okay, so y is asymptotic to 3, x minus 3 squared, negative 1. 4 cubed is 64. Oh, that's just gigantic. So y is asymptotic. We just really want its sign. Y is asymptotic to a negative 192 x minus 3 squared near x equaling 3. Let's do 2. So near x equal 2, we have y is asymptotic to, plug in a 2, plug in 2. If I plug in 2, I'll get 0, so let's leave this as x minus 2. Plug in 2. And so I get 2 times negative 1 squared, 1, x minus 2. 2 plus 1 squared, 2 plus 1 is 3, cubed is 27. And again, the most important is really not the numbers as much, because I won't be able to be that exact when I draw this, but the sign is important. So this is going to give me a 54 x minus 2. And lastly, let's see what happens near 1, a negative 1. Oh, and I guess I should say this, near x equaling 2. And so near x equaling -1, we have, well, let's get a little bit more room here. Plug in -1, plug in -1, -1. And again, if you plug in -1, you get 0. So let's leave it as x plus 1 cubed. So if this is asymptotic to -1. -1 minus 3 is -4 squared is 16. -1 minus 2 is -3. X plus 1 cubed. Negative times negative is positive. 16 times 3 is 48. X plus 1 cubed. Near x equaling -1. Okay, so let's try to sketch the graph of this. See if we can draw it straighter. Okay. So the roots are at 0. Two, 3, -1. Okay. It goes up into the first quadrant, down into the third quadrant. So my tails are here. So somehow it starts up here and goes down here. At x equaling 3, well, it looks like some quadratic, and so it looks like 3. Ooh, 3 minus 1 is 1. Okay, good. Okay, so, because I was like, wait, I can't do that. Okay, it's a positive. Okay, so near x equal 3, it looks like some big positive constant times x minus 3 squared. So it looks like a upward pointing, so here it looks like a parabola. So here it looks like some sort of parabola. I'm going to erase it. So here it looks like a parabola bouncing off the x-axis here. Okay, and pointing up. Next, at x equaling 2, it looks like a line having a positive slope near x equal 2. Okay. Near x equaling 0, it looks like a line with negative slope. So it looks like some line with negative slope. And near x equaling -1, it looks cubic. So it's going to look cubic, positive cubic. So it looks like positive times x plus 1 cubed. So it looks something like this here. Okay, so let's try to tie all that together. So it bounces. Ooh. Okay, let's try that again. I just slipped. Okay. So it looks, bounces, goes through like this. Okay. It goes up. Okay, so it looks something like this. So it's going to be much steeper by the way than what I've drawn. It actually goes up really fast, and so it's much more dramatic than what I've even drawn. But it looks something like this. So it looks like a parabola here, going a positive looking parabola, a positive looking line, a negative looking line, and then a positive looking cubic. So a sigmoidal that's positive. And so this is the graph of y equaling x minus 3 squared, x minus 2, x plus 1 cubed. Okay. And that's what that, the graph of that parabola looks like. Okay. Let me do problem number 26. Oh, okay.
I have a question.
Yes, yes.
What is the asymptotic behavior used for again?
It if you look really, just look really close. So zoom in at 3. The really close. If you zoom in at 3, it looks like a parabola. So if I actually just drew at 3, the graph of I forget the actual function here. It's the 3, 192. If I just look at the graph of y equal 192 x minus 3 squared, it looks something like this, right? It's a little steeper than that, which if you look here, that's what the graph of this curve looks like. It looks approximately like that. And so it's the behavior near the roots. So if you're looking close to the roots, this is what it looks like. Now, what I could do, and I'll sort of, so that gives you sort of, do you understand what that was? Let me ask you.
Do we have
So
to do this for every time we graph it?
no. It will be more important. No, as a matter of fact, what I'm going to do, let me explain it without doing the asymptotic behavior. So let me do it without doing the asymptotic. Unfortunately, you won't get this with that. But let me explain it how you do it without the asymptotic behavior. There's one part of the graph I won't be able to get correct because I'm not doing asymptotic behavior. So if I just did this without any asymptotic behavior, I would say, okay, well, it has degree 7. So everything goes into, adjacent quadrants. And here are the roots. And here is the multiplicity. And all I want to know is odd multiplicity for 0, odd even multiplicity for 3, odd multiplicities for the other 2. So everything is odd multiplicity except for at 3. So at 3, so now I can say, well, let's graph it. So I would say, well, sorry, it's taking me a while to scroll down. Okay, here it is. So now I have roots, so I just put the roots, -1, 0, 2, and 3. I know I go up into the first quadrant and third quadrant. Okay, so these are fine. I know that at 3, it is even multiplicity, so I know it bounces. So bounce, everything else is odd, so they go through. So bounce, goes through, goes through, goes through. So I get everything correct except here, I would without looking at the asymptotic behavior, I would just go through as a regular sort of graph. Now I can correct it, because if I look at the multiplicity, come on, stop. The multiplicity of -1 is 3, meaning it looks like a cubic, whereas these look like a linear equation. So what I would say is, okay, well, it's odd, and the leading order coefficient is positive, so we go up into the first and fourth quadrants. The root at 3 has multiplicity 2, so it bounces and looks quadratic. The root at 2, 1, so it goes through linearly, so it just passes through like looking like a line. The root at 0 is degree 1, simple. So it just again looks linear. The root at -1 has multiplicity 3, so it passes through looking like a cubic, sigmoidal. And that's what the graph looks like. So really all you needed to do is find the roots, find what the degree was, see what the sign of the leading order coefficient is, and then from there you can sketch it just looking at the multiplicities. Okay? Let's go on to the next problem. Okay, so problem number 26. Determine whether each function is even, odd, or negative. Okay, so let's do that. So we don't have to sketch it or anything. First off, well, I'll tell you. So to find if it's an even or odd function, let's first see if it's an even function. Actually, finding even or odd will be the same way. All I want to do is replace x by -x. So I just replace x here by -x. And so I get -x to the 6th is x to the 6th. -x squared is just x squared. But x to the 6th minus x squared is just f of x. And so this says that yes, indeed, this is an even function. Since f of -x is f of x. So this is an even function. It will be symmetric about the y-axis. And so it's an even function. Oops. Okay. This is an even function. Now, right off the bat, I could tell it's an even function because 6 is an even number, 2 is an even number. Therefore, x to the 6th is an even function. X squared is a function. Even plus even is even. So I knew right off the bat this was an even function, but just because I know it doesn't mean I can't just state it. I have to actually show it. And so that's how I knew function. Okay, let me do problem number 56. Graph each piecewise defined function. So a function is said to be a piecewise defined function if it has different formulas for different parts of its domain. And so notice that the rule for x less than 0 is take the absolute value. The rule for x greater than or equal to 0 is take the square root. Let me simplify this before sketching it. If x is less than 0, then x is a negative number. The absolute value of a negative number is going to be, well, you can't be x because the absolute value, because x would be negative, a number has to be non-negative. So you have to change its sign. So the absolute value of x is negative x if x is less than 0. So if x were like -1, you'd have to take its opposite sign to get a positive 1. And well, x is the square root if x is greater than or equal to 0. Okay. So now I want to sketch a graph of this. And I can do it as follows. Okay, that's kind of weird. So let's do this. This is x, y. So if x is greater than or equal to 0, it looks like the square root. Well, the square root looks like this. So that's the square root function. If x is less than 0, it looks like y equal negative x, which is a 40 at 45 degrees. And well, we keep going, but we only want to do this for x less than 0. And so this is the graph of y equals f of x. So it looks like a square root function on the non-negative side, like a negative x for the negative side. And that's what the sketch of graph looks like. Okay. Let me do problem number 60. So this was actually much faster than the other one. I didn't have to do that much. So problem number 60, evaluate each function at the indicated values. So let me give you some more room here to evaluate this. So for the first part, I want to evaluate, so f of the greatest integer function at of 3 of x. So let me do a, f of 4 is equal to 3 times 4, and then the greatest integer function. 3 times 4 is 12. Well, what's the greatest integer less than or equal to 12? Well, 12. So f at 4 is just equal to 12. Let me do part B. F at -2 and so this is just equal to 3 times -2, which is -6, and the greatest integer less than or equal to -6 will be, well, -6. It is an integer, and so f at -2 is -6. Let me do part C. So for part C, I want to figure out f at -1.2. So this is going to equal 3 times -1.2. Then I'm going to take the greatest integer less than this, which is -3.6. And I claim that f of negative 1.2 is equal to negative 4. Let me show you that visually. Okay, so if I look here on the number line, let's say this is negative 4, this is negative 3, and this is negative 3.6. I want to find the greatest integer that's smaller than or equal to negative 3.6. Well, the biggest integer that's less than or equal to negative 3.6 is negative 4. So this is the greatest integer. Which is less than or equal to negative 3.6. Okay. And so that's how I got that the greatest integer for negative 3.6 was negative 4. It always moves the number, the greatest integer function moves it to the left. It's the nearest leftmost integer. Let's do next one. So let's move this up. Okay, let's move this up, I guess. Okay, let's move this. Good. Okay, so it just says the graph each function. So let's do that. So, oh, can I graph? I can probably sketch the graph here. And this is the last problem. Yeah, so maybe I'll just sketch it here. Okay, so the function looks like, okay. And let's say that this is 1. 2. Okay, this is 1, 2. 1, 2. Okay, so at 0, it's 0. So if you plug in 0, you get 0. You're going to get 1. If you plug in any number in between 0 and a fourth, you're going to get, well, let's see, the greatest integer of a half is 0. So anything less than a half, you're still going to get 0. Then take numbers between a half and 1, but not equal to 1. Well, you're always going to get something that's the greatest integer value is going to be 1. Then 1 is going to jump up to 2. Until you get to a half. Okay, thank you. My computer keeps wanting to crash. Okay, now let's say this is negative a half. At negative a half, well, it's negative 1 up till we get to 0. At negative 1, it's going to be negative 2. And it keeps looking like this. So it sort of looks like I don't know, a staircase. Sometimes called a step function. And so it has this sort of, it keeps jumping and it looks like that. So this would be 3 halves. So it'll be 3 at 3 halves up to 2. So this is what the graph of y equaling 2x greatest integer looks like. Okay, and that is it for section 3.3.